something up here, and I'll give you a quick little intro. Because first of all, I want to thank everyone for joining us. I see we're still having a few people coming in. This is going to be our, I believe, 6th engineering and live presentation. No, 5th. Yeah, the 5th one. These presentations are opportunities for working engineers to talk about their careers or their career paths or current work, past work. Just kind of give students or those pursuing some sort of STEM degree or career something to look forward to, or give them an opportunity to ask questions of a professional who's working in industry currently. We hope you guys enjoy this presentation, and if you do, please share our Discord with anyone that you think might like it. We're also going to put this up on our YouTube channel later, so if you don't catch it all today, that's fine. You can always rewatch it later, or if you think someone else might be interested in this presentation, you can share it with them. That will be announced in our announcements channel when that's posted. If you have any questions about this presentation, please put them in the large meeting room, the text channel, and we will be creating a thread specifically for conversations about this presentation shortly. Sorry about that. This is being recorded. And again, that link will be shared when the video is posted. All that being said, thank you again for joining us, and I'm going to pass it off to Sways for his presentation.
Thanks, Chase. So thanks for coming out and watching this presentation. I hope someone actually takes something out of this. This is something I enjoy a lot, and I hopefully am trying to make into a permanent career. This presentation is about lithium ion modeling, predictions, algorithms, and using those kind of techniques to implement into our actual systems that use batteries, so that we can essentially use our batteries to their full capacity. We can predict when they're going to be essentially dead and need for replacement, and or used for predicting any sort of failures. I think this is a very interesting part where academia and industry actually combine and work in conjunction together at the same time. Usually what you see is research is done, and then maybe a decade later, you'll see that kind of work being implemented in industry. However, given how quickly battery technology is moving, this is a field where you can actually do this sort of academic research within the industry as a profession. It gets pretty involved, and so I think it's really interesting for new engineers coming out of school, seeing that this kind of work actually exists within industry, and they don't have to go remain in academia forever. So we'll go through this. I'm using this more of like an introduction to this topic. There's a lot of math. I don't want anybody to actually get focused on the math or any of the algorithms. Just getting the general gist of the whole idea is really important. If anybody's interested, we can always go into more detail later on for another presentation. But this, I'll be going through this. I'm going to talk about essentially why we're doing this and on how we do it, and then for the further actions. I have some quick little simulations I made for this presentation, and they're not much, but it will give you something that shows how this actually is implemented. So for now, lithium-ion batteries have become like the staple battery chemistry that we're using in our energy systems. I think it was actually projected that by last year it would be like a $40 billion industry, and I think it's actually more now. Almost every field within engineering, or not just engineering, but just any field, is in dire need of using more advanced batteries, and so there's been a lot of work behind actually how to improve our batteries. Now we have different topics in research and within batteries that we can go through. We can go through characterization and benchmarking. So essentially, the battery in our hands, how does it work? What are its benchmarks? What are its limits? We have things like modeling and control, which is what we're going to be talking about today. More characterizations on the electrochemical, electrothermal side, which means that we go into the actual battery itself and see how all the different functions within the battery work. Aging characterization. So how does a certain battery age? Every battery chemistry ages differently, and the more batteries you have within a pack, the pack itself ages differently as well. Prototyping and manufacturing design. This is something I'm going to go out to at the very end. It's really interesting. The I would argue that the biggest downfall with battery technology is the actual manufacturing design part. This is because of the intense process it takes to actually develop one cell. And so within those processes, and since it's all mechanical processes, you have physical damage that happens throughout the battery life within the manufacturing process. And those little kinks and quirks actually bite you when you try to actually implement the battery within a system later on. And so it's hard to actually detect that kind of stuff. And so we have a lot of companies like BMW working on more intelligent ways of actually how to manufacture batteries. Microstructure research uses essentially different techniques to actually look at how to model the micro at the nano material and the micro material level of batteries and see how to actually form new ways of developing batteries so that we can extend both the life and the capacity of a battery without changing the chemistry. So, like, what kind of materials instead of graphite or lithium can we use, for example? Testing facilities is something I do at work. This is where we actually abuse the batteries past their limits to see how do they actually react to different situations, so that when we implement it into our system, we know exactly what's going to happen, and we can design our system so that it can mitigate that. And then diagnosis and prognosis, something else we'll be talking about today mainly. This is essentially giving our system a little pointer about what our battery's health is at this current moment. And so we'll be talking about diagnostics and prognostics and modeling and control. By control, I mean control theory, and we'll get to it later, where it's essentially how to actually make the battery do what we want it to do, while we're reducing the negative effects of it. So this is a Ragon plot showing why lithium ion is very popular within our battery technology. If you can look on the bottom, we have specific power and specific energy. And essentially, specific energy is how much energy can it store. Specific power is how much energy can it actually provide and how fast it can provide it. And lithium ion chemistry batteries are essentially giving the best of both worlds. Everything else either is mainly an energy battery or a power or energy cell or a power cell. Lithium ion can produce both. So essentially, it does not have a defined role. The only way it can be swayed to either one or the other side is the way we actually pack the cell together, if it's cylindrical or if it's rectangular. Other than that, lithium ions are really useful for this kind of situation, because now you have a battery that you can recharge, and it does not reduce its life drastically as compared to the other batteries, and it can produce a lot of energy within a short amount of time. So you can use that to power something like a vehicle to go as fast as you can see how fast Teslas can go. That's due to the lithium ion chemistry itself. But lithium ions do come with their own defects. Essentially, given all that good information you have from lithium ions, the other effect is that it's hard to actually maintain. They're very explosive. They're very high energy densities cells, and also the mechanisms behind how they age and how they go into, I guess, these abusive situations is not really understood. As you can see on the right, I have an image of something we do at work. This is essentially just heating up the cell at the at the anode of the body of the cell, and just by heating it up to I think 70 C, this is just one cell that causes this sort of thermal runaway. Thermal runaway is essentially this explosion of energy. Same thing on the left-hand side. And then this is a robot JPL that essentially caught on fire based on bad battery design. So these kind of situations we kind of want to, stay away from, especially when we have things like our phones that are heavily reliant on our lithium-ion batteries or future electrical vehicles, where they're reliant on these lithium battery chemistries. And so in order to actually test these kind of situations, we go through stringent testing. These tests can take for a while. They can take a few months, few years. If it's like a satellite program, these battery tests can take up to 15 years. I don't think anybody actually has the time to sit around waiting for this kind of test to be finished so they can say, all right, the test shows that this battery will be fine for our mission. The testing is actually very expensive as well, and there's not many different centers that actually do this kind of testing as well. The other issue with this is that as we go throughout the years, we get newer and newer cell chemistries. And so right now we're looking at solid state batteries. Well, solid state batteries are, if they are developed now, we've been working with lithium ions for, I don't know, 10, 20 years. All that data that we have, it's kind of not relevant anymore. And so now we spent all this time, now we have solid state batteries, we have to basically repeat this process again. So as you can see, this can be an issue within industry where there's basically there's a lot of information and a lot of need for something for like these advanced battery systems, but we don't actually have the data or the capability to do it yet. So something has to be done. And so in order to attack this kind of problem, we can look into using models. So we can essentially replicate this kind of testing and these kind of thermal runaway events and see how actually how interacts with the system, and essentially not need to go through this kind of stringent testing or reduce the amount of testing we need for these kind of batteries. So that's what we're going to be talking about today. It's actually how do we take all this kind of testing, push it to the side, use simulations, use models, use the algorithms to provide some sort of prognostics so that we can reduce the life of so we can reduce the issues that come from battery degradation within lithium-ion batteries. I kept seeing battery degradation is bad. I want to just talk about why it is bad, because I don't think it's clear until you actually see it, and it's actually happening within your, let's say for your phone, every time you charge it and stuff. I don't think anybody actually realizes this stuff is actually happening. But a battery works essentially by, I don't know if where's my pointer? So essentially we have an anode, usually made out of some sort of copper. We have our cathode, some sort of metal, usually aluminum. We have our, this is the current collectors on both sides. And then the green spheres and these hexagonal shapes, these are the anode and cathodes. The red dots are the lithium ions. And essentially what's happening is that you have these different layers. These are just basically layers and layers and layers of graphite and aluminum. Graphite and some sort of metal, lithium ion metal, that essentially let lithium ions, the red dots, to actually get wedged in between, depending on if there's a charge or a discharge. And so the two different, so the anode and cathode are separated by an insulator. It's a porous material. And then within all of this is the electrolyte. So it's a solvent where it allows the lithium ions to basically transfer from cathode to anode, depending on if it's charged or not. So if you actually open up a cell, let's say any sort of cell, this is like a 18650, I think. 18650 means the length is about 60 millimeters, the diameter is 18 millimeters, and the 0 at the very end means it's a cylindrical cell. So 18650s, if you actually open it up, it's just a roll of these different layers. So we have our copper anode over here. We have the copper current collector. Right next to it is the anode itself. Then we have the separator. Then we have the cathode, and then behind it will be the aluminum current collector. And these are just rolled and rolled and rolled and packed and packed and packed into each other and crimped into one cell or a pouch cell. But so depending on how many rolls of this you have determines your capacity of your cell and how it's actually designed and how it would actually go into the runaway. So this design is very important, but that's for a different topic. Regardless, as you charge and discharge your cell, what you're basically doing, you're essentially causing both chemical and mechanical fractures within your cell. So some of the things that happen is electrolyte decomposition and reduction. So this is basically the electrolyte that's within the cell that allows the lithium to move back and forth, gets reduced through any sort of inert reactions. So reactions that don't actually provide the process of, that are not important to the process of how batteries work, but there are what we call side reactions. They're just on the side. These are reactions that take in lithium and the electron molecules to essentially create a new inert molecule, which causes the battery to have less electrolyte concentration, less lithium ion concentration, and thus the amount of capacity it can provide gets reduced. The SEI, the solid electron interface, essentially is a very, I would say, I think it's one of the most interesting phenomena in batteries. And what's basically happening is during the first few cycles that you charge your battery, at this very interface where we have the anode, the solvent anode interface, there's basically like a shield that is formed around it. So the graphite anode reacts and forms the deposits on the layer. So these are like deposits of lithium ions, ion aside. And so what this does essentially is that it's like a layer that prevents any sort of like it prevents the sorry, let me rephrase that. It prevents the electrons from entering and exiting from the anode. Usually it's usually on the anode side. And what is happening is that it just forms this layer, but it also protects it from any sort of reactions with the electrolyte. So it reduces the loss of lithium, but also uses lithium to form itself. So as we charge and discharge over and over again, this layer keeps growing and growing and growing. Well, over time, what you will notice is that these lithium ions that are are basically layering on top of each other create these sort of like what we call lithium dendrites. They're essentially these pointy objects that you can see over here. And what happens is they can rupture the separator. And now you have a direct connection from positive and negative. You essentially created a short. And so infinite current technically would go through the cell and blow up. And this is something that happens naturally within the cell. So it's not something that you're doing other than charging and discharging the battery. So the SCI is actually dependent on how the cell is actually charged, how fast it is, slow charging, slowest charging, or what the temperatures around it are as well. Binder decomposition. Binders are what attach the anode and cathode to their current collectors. So over time, the binders do react with other molecules and electrons to form some sort of inert molecule again, and now you have less current delivering process capacity within the battery as well. Active material dissolution, gas evolution, and lithium plating dendrite growth. So this is what we all talk about. Essentially, there's a lot of processes as the cell is working correctly. On the side, there's a lot of reactions that are happening that are removing all of the necessary atoms and molecules needed for this process. So it's a self-degradation process in a way. The mechanical aspects are a little bit more intuitive. Basically, when these lithium ions are being wedged between these different layers, you're causing both volume changes. So basically, you're creating situations where you can cause fractures within these in these little different layers. So the more fractures there are, there's less places that lithium ions can bind to, and if there's less places that lithium ions can bind to, then less charge can be held by either the cathode or anode. And so now you have a battery where essentially it can't provide as much as capacity as it was designed to. So what can we do? We can use different metrics to essentially tell us where the battery's health is within its current time. So given that all those reactions that I just talked about happen, there are a few different metrics such as state of charge, state of health, remaining useful life. These kind of different metrics can tell us, all right, based on what we are doing with our battery and based on what we know about our battery, what should we do? Essentially, give us some way to actually decide what do we do with our batteries. Do we change it out? Do we charge slower? Do we include pulses in our charging? Do we do we put it into a different system? Do we reduce the temperature? But the issue is that this kind of stuff is done through current technology with like BMS integrated circuits, different ICs that you can buy from like TI or Analog Devices. But what they do is that they are not actually taking into account these processes. So what the current technology is doing is that they take either, for example, I have here the battery limitation. So on a data sheet, it will give you what's the maximum voltage, what's the minimum voltage, what are the maximum temperature ratings that you have, and it has these hard thresholds. If it goes above, shut it off. If it goes below, shut it off. If it's in between, you're good. The little bit more complicated ones are under the premise of Coulomb counting. This is basically an integration method that calculates the capacity of our battery. But the issue with integration is that this is not based on physics again. This is just based on lookup tables. So lookup tables are just basically heuristic tables that you develop over testing. So you say, all right, at 100% state of charge, our voltage was this. At 50% state of charge, our voltage was this. And you use that, you give it to the Coulomb counter, and it can integrate your current measurements and relay it to that table and say, all right, our state of charge right now is so-and-so. But this is very inaccurate, and inaccuracy means there's errors in your calculations. And errors within integration means that they accumulate. So after so many cycles, all of the errors that you've had from day one until now have accumulated, and now your measurement is actually not reliable anymore. And then impedance tracking is something new. It's still weighted. I mean, it's still done through the essence of Coulomb counting. Impedance tracking is looking at the impedance of or the resistance of a battery, but it still follows the premise of Coulomb counting. So the same error issue, the accumulation issue persists. So what is the solution? And this is the premise of the whole presentation today. The solution is to essentially use different kind of model, a different sort of model based on physics of the battery, and we can use that kind of stuff to actually provide prognostics to our system, so our system can automatically make decisions on how to actually work with our battery. So this is a simple flow chart. We're going to be revisiting this over and over again throughout the presentation, so no need to take it all in right now. But we're going to work with history data. So history data means data that we have collected before implementing the battery, and data that we have right now, meaning the sensors on the batteries collecting some of the data. We develop our different models. So today we're going to be talking about electrochemical and ECM models. Empirical models are just essentially what you would see in data science, where you don't actually know the physics, you just model it based on what you measure. We take this and we filter some of the data. Filtering in this case, you can think of it as removing noise. What we're doing is removing uncertainty. These are probabilistic methods. So we're looking at not noise in terms of like, analog signals, but we're looking at removing the uncertainty that we have of a given state of a battery. We develop our state equations, initialize them, and then actually do our predictions over here. So first, we're going to look at how to get our data. So the issue with batteries is that we can only make, I think, 4 measurements. We can measure the voltage, we can measure the current, the power, and the temperature. So that means we can input voltage to the some sort of constant voltage to our battery. We can input a constant current or constant power. And by constant power, I mean you regulate voltage and current, so you can maintain a certain power. And then we can also change the ambient temperature around the cell. And then our output is actually the same stuff. So how do we actually get all of that information that we just talked about in terms of degradation within a cell just with these four parameters? And so what we're doing is we're going to basically figure out what states are we going to use to represent those kind of processes. So when I say states throughout this presentation, what I mean is I have a system. I have a dynamical system. This means that it changes over time. A battery is a time variant problem. So what we do is basically say, all right, what are the key defining processes within a battery that define what we're trying to measure here is degradation. So we can say our state of charge, which is 100% state of charge means your battery is fully charged. 0% means it's not. The state of health, basically how much capacity can it give now at this moment, rather than what it started with. The temperature, the impedance, and voltage, current, power. These are all different states of a battery. So at this current moment, the time equals right now. If I look at my battery, what is my voltage? What is my current? What is my power? These are different states of the battery. What is the state of charge? So at this current moment, how much charge can it provide me? So we're going to use these parameters and try to essentially develop our different models. So to develop our models, we need to essentially initialize them with some sort of previous knowledge. And so there's different testing that we can do for batteries. Destructive physical analysis, short for DPA. This is essentially, we take a battery, we discharge it all the way, and then we essentially open it up. We open it up, we roll out all the different parts of the battery, which we call the jelly roll, and we do physical measurements to say, all right, well, this is what this particular cell was measured to be. We can do different cycling methods. So pulse cycling, for example, where instead of charging it at a constant rate or discharging at a constant rate, we include pulses. EIS, this is you see how the impedance of a battery changes with any sort of AC signals that go through the cell. And then you can use like Nyquist plots to essentially see what that means in terms of internal reactions. Calorimetry, tomography, GIT, GIT, so forth. There's many different tests that we have. And so depending on the model type that you want to create, you can select it. There's select tests that you use to generate those kind of models. And so for the purposes of this presentation, we're going to look at electromodeling and electrochemical modeling. And so first, looking at electromodeling, we're going to look at different ways of cycling the battery so that we can get the parameters for our model. One pretty common way of doing our cycling for model generation is random walk. All that means is that we introduce the battery to go through a very randomized sequence of inputs so that we can characterize the battery over a range of uncertainty that it can possibly experience. And so in this kind of data set that I was using, the current essentially jumps between 4 amps to -4. And then every 5 minutes, a current value in that range is selected. So it will be basically at 4 amps, and then every another 5 minutes, it would jump down to -4. Another 5 minutes, it would jump back up to 4 amps, 4.5, sorry. The battery's charged to 4.2. That's because these are 18650s. 18650 cell is what you typically see in like a Tesla car, your battery pack on your computer, on your laptop. These are the more common lithium-ion batteries cell sizes that you see. So the maximum voltage usually for 18650s are 4.2, and the minimum cutoff is actually 2.5, but they don't tell you that because if you get to 2.5 and below, you basically kill your battery. And so manufacturers will tell you that the cutoff is like a 3 volts, just to keep the consumer safe. This data set that I worked with went down, they cut it off at 3.2. Not sure why, but it's okay. It's as long as there's some sort of threshold. And then between each current selection, so between the -4.5 amps, there's a 1 second rest, and then it continues with the pulse up to 4.5 amps. And so this happens and there's 1,500 steps. So this happens 1,500 times over the course of time. And right afterwards, after every random walk sequence that we have, a constant current, constant voltage cycle is performed. This is the most common way of charging and discharging a battery. Constant current, constant voltage, all that means is that we have a constant current applied until the voltage of the battery reaches 4.2. Then once the battery's voltage reaches 4.2, we hold it at 4.2. And then, so, sorry, let me rephrase that. We apply a constant current to the battery until the cell reaches 4.2. That's 4.2 volts. That's your constant current part. And then constant voltage is when you hold it at 4.2 and you discharge and taper the current down basically to zero. The reason you have to do this is because that when you charge, think of like a spring mass system. If you are essentially pulling a spring all the way back, there is a tendency for it to basically jump back back to its original state. And so that's what kind of, you can think of it like that in a battery. As you're charging, as the cells go from anode to cathode to anode, they're essentially being pulled from their resting spot. And so essentially when you get to a fully charged state, like a 4.2, if you just turn it off and you don't taper the current down to zero, what you see is that within seconds, your 4.2 is going to become like 4.19, 4.189, 4.8, and then just back up to 4.9, and just back down to 4.17. And so it's not going to stay at 4.2. And so there's some situations where you actually need exactly 4.2. And so what you do is you taper it. So as you taper the current, you're essentially letting it fluctuate, but applying smaller and smaller amount of current until it stabilizes at 4.2. So in this data set, the current tapers down to 0.01 amps, and then a rest period was added between the random walk and this CCV cycle. The rest periods is what we call voltage relaxation. It tells us essentially the true voltage of the battery at the current moment. And so what I have plotted here is just the discharge and then the actual rest period right afterwards. Discharges are what's more important for our purposes. But this is also a reason why your batteries on your phone charge quicker and die quicker when they're older. If you look at this chart, the first cycle, the very first discharge, and same for the charge as well, that happened was this very first line at the top. As the battery ages, you're looking to see this line actually shift backwards and be further on the bottom. All this is that if you think about the battery like a bucket, and you have two buckets, one without rocks inside and one with rocks, and you want to fill it with water, which one would fill up faster? The one with the rocks. And so if you think of the rocks as the internal resistance that's building up because of all the different side reactions we talked about and all of the inert molecules that are resulting from those side reactions in the battery as the battery ages, those impede the flow of the lithium ions from cathode to anode. So essentially what you have is you have a lot of things blocking the way between the cathode and anode, and it's harder for the battery to actually produce the energy it needs. And so that's what you're going to see here is as the battery ages, it charges much faster because there's less water in the battery. And then once you want to discharge the battery that's old, it's going to discharge much faster because there's, again, less water within the battery. So taking this kind of information, we also applied so after every random walk sequence, after 2 cycles of that, so random walk, charge, discharge, random walk, charge, discharge, we do a pulse charge and a pulse discharge. All of this is doing is to give us information about the internal resistance of the battery, which I'll show you in a quick moment. Essentially, there was a quick discharge pulse that's applied and for about, I think it was 10 minutes, 10 minutes, and then it goes back to discharging as normal. And so all the reason to do this is that the pulse information, so how the time between this pulse and back to relaxation gives us information about the internal resistance. A lot of the battery systems that we have right now in our, let's say, for example, cars, any of our smartphones, it's doing this on its own. You don't really realize it because it's happening really quick. 10 minutes is a lot. This is very extreme. Usually you might just see it for like 10 seconds or 5 seconds or something like that. So it's not really, you're not really seeing it happen. But this is something that our systems do to make sure that the resistance within the battery is within range. So taking this information that we have, we've made sure that the information, our data is random enough so that we can generate a more generalized model. We're going to take this data and we're going to create our the two different kind of models. First, we're going to look at the ECMs. So these are these are the battery equivalent circuit models. So one way to model a battery is to treat it like an RC circuit. This is the first order. A second order would be another pair of this parallel combination, another resistor in series. And so usually you might see these as a second order or a third order. Usually any more than that, it's not really needed. It's not really adding much. But I want the key thing I want everybody to get out of this is that our system is nonlinear. So the reactions that are happening within a battery are not something that you can measure linearly between and have a great little simple relationship between, state of charge went up, that means our voltage is down. It's not, we can't do that. And so what we've designed here is a state space model of our RC circuit. So we're using this information over here of our topology and the information that we know about through battery research about how to actually define state of charge and how to actually define the the interfacial charge between the different surfaces, the resistance that comes from that. A lot of the information comes from our pulses. So the pulses that we did before, these little parameters can fill out a lot of our constant values over here. And so this all comes from what we were just doing right now, the different pulses. And then the model parameters that we're trying to identify, here I have all these listed. Hopefully when, I don't want to get into it because it's going to take it too long. But if anybody is interested, you can look at the recording and look at what all these different parameters are. But essentially what we're doing is we're measuring the voltage of the battery. So the terminal voltage, the VT, and this is based on this relationship here. And using that, we're going to look at our state, our two different states. So the VP is our voltage across the battery, and then SOC. So the point of this whole experiment was to figure out how to predict and measure the state of charge of a cell. So as I said, the states of the battery is what the battery is currently experiencing. So each one of these have their own relationships, and our measurement is what we're actually measuring. So our VT is what you see when you put a multimeter across a battery. So as we get that data, we relate it to this, and we can input it into here, and that's how we essentially develop our state space model. Other than ECMs, what we can use is electrochemical models. These are physics-based. So these are physics-based as well, but they're only looking at the electrocharacteristics of a battery. Electrochemical models look at the essential. They look at the rate of transfer, where the molecules are, and the different energies that come from these reactions within a battery. So one particular model, the single particle model, is a very common way of doing this. And what they're doing is essentially they're looking at the anode and the cathode, and they're taking just one of these, let's say one section of the actual cathode or anode, and saying that's the entire anode. So it's a big simplification, but with that they use the Butler-Volmer kinetics and Fick's law for diffusion. We develop. I didn't write all these yet. They're in a different slide, but it's a series of differential equations that we can essentially approximate, solve for, and use that to predict our different states of the battery. Currently, what people are trying to get working is the pseudo two-dimensional model. This is the P2D. This is something I think only UT has been able to do successfully, but the P2D model is essentially the same as the single particle model, but we're looking at the different gradients between these two layers. So we're actually looking at the reactions right at the interface between separator and anode. This is something that is disregarded in the SPM. So this P2D has, I think, generally around 30 differential equations that are all coupled. And so it becomes a very difficult task on how to actually use this model within actual systems. We're getting close. So the main takeaway from this is that now you have much more information on the physics of our battery. How do we actually compute it? This is where I'm stuck at, and so this is what I'm usually doing at my work. I'm basically taking the framework developed by Dr. Venkata at UT Austin, and how do you actually take those huge coupled nonlinear models and actually solve for them? And so there's different ways to actually approximate these. Here's a few different versions of it. Dr. Venkata created like this Tankin series method. I have to still understand what he's doing, but essentially being able to actually solve this is what's crucial. And so the issue with doing so is that this is all just for one cell. And so the problem with batteries is that everything I just said is fine and dandy, but that was only for the cell level. These models do not hold for anything that comes down to a millimeter, micrometer, nanometer level of batteries, nor does it work for bigger battery packs. So we're essentially in a position where we're looking at different scales and different times and different phases of our chemistry, and we're trying to generalize this. It's not possible. We cannot generalize these models for everything. However, what we're trying to do is say, can we develop hardware so that we can calculate these sort of complicated models for each cell within a big battery pack, right? And so that is the ultimate goal, is essentially how do we take, so like, for example, this is the Tesla, the bottom of a Tesla. I think there's 1,700 18650s in here. And each one of these rows have their own BMS system, the battery management system. Is there a way we can actually reduce this complexity so that we can run these algorithms properly for each cell within a pack this large? And I've been told it's possible. I still have to see it for myself, but that's the current work that we're trying to do. How do we actually now predict those certain states, like state of charge and state of health? So we've developed our electrochemical model, we've developed our ECM model, and now what we're going to use is sort of prediction algorithm. In this case, I used state estimation. So Kalman filters, particle filters, these are things that have been used for decades among decades. It's why we got to it's how we got to the moon. It's how we have self-driving cars. It's how robotics do what they're doing. And it's the same application here. I'm not going to go into the math. This is a unscented Kalman filter. This is something that you use for a nonlinear system where you don't want to linearize it. So it allows you to essentially take the distribution of values that you have. It takes the mean and it takes the most representative points around it that represent the entire distribution of your data. So these are called sigma points. It goes through a nonlinear transform. That is your nonlinear equations. So the nonlinear equations that we have over here and the nonlinear equations that we have over here, you feed it point by point, which bypasses the need to linearize. And now what you have is you have an approximated solution around the same sort of distribution. All that means is that basically we're taking our data, we're using the current measurement that we have right now, we're looking at what we had before up to that point and say, all right, what could be the next point in our data set? And so I simulated this. I used the ECM for predicting the remaining useful life of a 1860 cell, and I used the same UKF for looking at end of discharge voltage. So remaining useful life is usually set to be 80% of your starting capacity. So I don't know if anybody has an iPhone. I'm not sure if Android phones say this as well. I'm pretty sure they do. They say that after 80% of your battery health, it's no good. You need a new battery or a new phone. That's where this is coming from. This is something that just in the battery world is accepted from what I can tell. I'd like to be wrong. But anyways, the blue line is what we predicted. The orange line is what the actual measurement was and what the actual cycle count was. So I think this was 200 cycles, and we're about 19 cycles off. And I'll get into why this discrepancy is there. However, the main takeaway is that we actually were able to get pretty close. 20 cycles is actually pretty good, being within 20 cycles, because 20 cycles can happen, within like a week. So it's not too bad. And so if you're looking at a long mission, for example, like a satellite mission or something, if you can predict ahead of time, weeks and months ahead of time, that this is how many cycles we're going to get from this one cell, then you can plan ahead on when to replace that battery, for example. And the discharge voltage is also, we're trying to basically figure out what is the actual ending voltage once the battery's discharged fully. As again, we're about 6 minutes off as to when it would reach that ending voltage versus what it actually was. So end of discharge voltage means, hey, I'm at the very last discharge cycle. This is the last stretch. How much longer can I use this battery before it completely dies out? And so we're about 6 minutes off. But again, the same reason why we're off here will be the same reason here. And I'll get to that at the very end of the presentation. Okay. We've modeled our system. We gathered our data. We modeled our system. We made our predictions. So what? The whole point of this is to actually integrate this within our complicated system. So for the car, or a renewable energy source, or a chemical plant, anything that requires any sort of big batteries. And so there is some interaction between batteries, some electronics, some mechanical systems, and so there's going to be some sort of loop, a closed loop. And what the whole point of this presentation is how to actually implement these physical models within a closed loop feedback system. I don't know how many people are familiar with like control theory or just controls in general, but controls is essentially a feedback system where you look at what your system is and you want it to be a certain threat. You want to regulate it to a certain output. And so you're basically forcing a system to do what you want it to do. The point here is that what we can do is we can take our battery, we can take the measurements. So as we said in the beginning, the voltage, current, power, temperature. We input that into our physics-based models. So the SPM, P2D, the ECMs. We get a certain output. These outputs are fed into our estimator, the one I just covered. So the unscented column filter, the particle filter, EM. And then we input these with some sort of constraints into a MPC controller. MPC is something that was developed by chemical engineers decades ago. It's used heavily in the chemical engineering departments. Most of our chemical plants have MPCs running. MPCs also, which if you look at Boston Dynamics, and you're wondering how those robots are doing anything they're doing, and none of it's machine learning. It's all MPC control. How different self-driving cars are moving around. It's all MPC. MPC is a very powerful tool. It's essentially a optimal control that uses optimization and constraints that you can use to develop a control action. This control action will go to a power supply. So in this case, we have this LLC resonant converter, which provides some sort of power to the lithium ion battery. So either it's charging it or it's doing something else with it. And so what this control action is doing is telling these like switches how to switch to provide a certain output to the battery so that the internal resistance for the battery, for example, does not increase beyond this sort of rate, or so that the state of charge remains at a certain level, or for example, the state of health doesn't degrade as fast, or so that extends the remaining useful life of the battery. So all the things that we were predicting, we can actually use that, give it to the controller and say, look, operate yourself in a way to extend the life of this battery. They extend it, which in the case will also will increase the safety of the battery as well. And so, I forgot about that. Essentially what we do is essentially add this feedback here, and this feedback will talk to these switches. Just a quick example on how this works. I have another simulation. This is a balancing problem. So cell balancing is a pretty big problem, especially when you have a series of cells in a pack. And the need to balance our cells is because if you have, let's say, five cells in a string, and each one of them are at different charges, different state of charge. So let's say the first one is at 100%. Some of them are like a 98, and then there's one at the very end that's at, let's say, 50% state of charge. Well, the amount of capacity that this battery pack can provide is reliant only on that one that's 50%, because once that is done, once that is basically at 0%, it doesn't matter if the other cells have the capacity to provide. That battery will essentially disconnect the whole battery from the system. It's also a safety concern. You don't want to go below a certain threshold on a battery voltage. So the limitation is on the lowest cell. So if everything is at the same state of charge in a series pack, then you're good to go. But that requires some sort of balancing. Now, there's different ways to balance. Over here, what I have is called a cell to stack balancing. And this is active balancing. Active balancing means that you have actual circuitry that uses switches rather than like just putting a resistor across the battery and draining current. This is to increase efficiency, reduce any sort of loading, negative loading effects on the cells. And all that's happening is essentially that the batteries, when they have too much charge compared to the rest, they provide this to this transformer. This is a coupled transformer. And so what we have is that we have a current flow. It gets stored in the secondary of the windings. Once it's charged, once the switch is off, then that charge is transferred over. This goes to the stack. So I said cell to stack. So it's going from the cell, then it is transferred over to the stack. Then the stack feeds the entire string of cells. So that's all that's happening. You have each cell providing some bit of energy over to the stack, and then the stack provides the rest. So everybody gets the even amount of charge. And so this happens until everything's balanced, and then you're good to go. So MPC, I don't want to get into the math here, but the premise is that we are solving an optimization problem with constraints. So we have our main problem, which is minimize the time to balance given the set of initial state of charges. So we have the initial state of charge of each cell. Let's say one is 100%, one's at 50%, one's at 60%, whatever. And we want to minimize the amount of time it takes to actually balance them all. So minimize them such that at the final time, there is no unbalanced state. So keep doing this until there is no more unbalanced cell within our battery pack. And then the energy transfer to and from the converter stops. So basically, once we get to that balanced state, stop, essentially. No, don't do this anymore. And then we define the balanced state as there's only 3% variation between each state of charge. 3% is pretty lenient. It was just for practicing, but usually you want to, depending on the situation, you might want this to be much smaller, actually. And then this is a general MPC framework, but all this is doing is basically taking the topology that we're looking at. This is the topology that we're working with. It's a flyback converter, a bunch of flyback converters doing our balancing. So all that's taken into account into our calculations. And some results. So the average balancing means that I basically did not use MPC. Average balancing means I looked at it from what a current technology would do. It would say, all right, I has to have a threshold of, let's say, 50% state of charge, and 50% will be the average of the initial state of charges that I have. So the initial state of charge, some of them are, one is at 82%, one is at 59%, 63, 42. Usually it's not like this in real life. They'll be much closer, but I just wanted to be very aggressive with this to see how robust my algorithm is. And it took about, it was 110 minutes, and efficiency wise, how efficient the converters were in terms of power loss, 42%. The switching that was happening was much more aggressive here because it's not optimal way of doing this. It's looking at just, hey, is the battery at 50%? No, keep going. Rather than using actual MPC, using the same initial conditions, it took about 60 minutes with 75% efficiency, so a increase of 79% in efficiency. And the switching was done in much more calm manner. It was not as aggressive. It was off and on when it needed to be only. Here we can see that the fluctuations at the very end, when they're all the same, is maintained to be basically relatively the same. And lastly, this bar graph is just showing the discrepancies between our blue and the orange. Blue means the initial state of charge. The orange is when they're balanced. This is using the MPC control. And so as you can see at first, the differences between the different state of charges in the blue, very off, very skewed. Essentially at the very end, they're all equal. Average balancing, there's still a discrepancy between the balanced states because it could never settle. As the charges fluctuate, it's usually that 3% threshold that we're setting was not always met, even though technically they were balanced. So I went ahead and I tried to validate this a little bit more with more extreme versions of our state of initial charges, state of charges with MPC here. But we basically are seeing the same thing. Essentially, everybody stabilizes at the very end at one threshold. Same over here as well. These are different state of charges than before, but basically the results were the same as compared to average balancing. So these validation sets have their own state of initial conditions, but as we can see here, over here, this was MPC around 120 minutes. It was balanced. On average balancing, it was closer to like 200 minutes. They were balanced, and then over here I could actually not get them to stabilize at all towards the end. So this actually never balanced throughout the entirety of the simulation. All of this I'm actually implementing with these different components. These are actual, kits that I can buy and use them at work. Essentially, what we're doing is seeing how this would work for our situation. I work in aerospace, and a lot of our missions in the future will be deep space. And the issue is that the systems that we have operating on batteries, they are in operation for a very long time. Sorry, they're not in operation for a very long time. And when they are, that's just a quick little, maybe if it's a EVA, they go outside for a couple of hours and come in. So we're trying to actually see how to implement all this, and how does having less data affect the validity of our approach. But if anybody's interested, look at the video later. Looking to see if you can buy something like these and try out these kind of algorithms. MATLAB has a lot of examples on how to use MATLAB and Simulink into developing these sort of models and implementing them on their preferred hardware. This is just what we were using, something we found. And so what is the future of this? Well, okay. Remember when I said I was going to explain the discrepancy in our simulation results, why we were off? The main issue is that as the batteries degrade, the models are not being updated. So as they degrade, those parameters change inside of our models. And if the model is stagnant and the battery itself is changing itself, we cannot actually correctly capture what the battery states is currently, even though it's closer than what we have currently in our current technology with Coulomb counting. What we can't do is essentially do the same. We can't apply the same model throughout the entirety of the battery. So what has to happen is we have to update our estimators. We have to update our predictors. We have to update our models so that we can actually follow through with the battery. So a lot of these future work is essentially using adaptive techniques in our estimators, using something like EM to update the model parameters. So my plan is to use both hardware and cloud. Hardware to do real-time estimates and predictions, feed that to something like the EM algorithm to run in the background on cloud offline, so it can find out since it's much more computation intensive, do it on cloud and see, all right, if anything has updated in our models. If so, update the real-time model with that. Using MPC for fast charging, that's what UT Austin is doing. And this is what currently a lot of companies like Tesla, Apple, and a bunch of different, startup EV companies are trying to implement into their technology at the moment. So up to now, as I said, we've been talking about battery cells, so just one cell itself, but we still have to tackle the problem for batteries. And this is where the next point comes into play: machine learning. Machine learning is can be very critical in terms of approaching the battery issue and more. What we can do is that we can integrate a hybrid approach. Essentially, we're looking at a model-based, data-driven model, a data-driven approach to our intelligent battery management systems. So, what machine learning can help with is, hey, I need to figure out, this is my, let's say, P2D model. I have 30 dynamical equations. Which one of these is actually important? Do I actually need all these equations because it's taking too long to compute? Also, it can improve our estimators. It can improve our controls by basically, there's a lot of techniques called learning control. So we can take MPC, apply some machine learning techniques to it to basically optimize the different parameters within a control framework. We can optimize our estimator, so like the Kalman filter has a lot of different constants. Well, machine learning can help us figure out what's the best constant to use rather than us trying to heuristically figure out, well, let's make alpha 1, let's make beta 2, see what happens. Machine learning can automate that for us and make it much faster. And the other thing that machine learning helps with is with the future of the battery data bank. So NREL is a national lab in Colorado with here at NASA, and a bunch of different universities are working on creating a large scale battery data bank. That should be like a big relational database. And all this is to essentially have everybody upload their results, essentially, so that we have enough data to develop much more accurate models, rather than waiting 10 years for a battery test to finish. Maybe someone else has already done that, and so we can take their data as well and work on our models based on that. And so what's happening is that it's not just universities and these national labs, excuse me, but also there's been a lot of talks with automobile industries, that pretty known ones, I won't name them, that are willing to provide this information, because they cannot wait that long or have the infrastructure to do this sort of testing as well. So this is where I was talking about in the very beginning of the presentation, where it's interesting to see this position where academia and industry are working together at the same time, working on solutions that can be implemented at the same time as well, rather than waiting for some academic solution to be validated for years and years before it's found its way into industry. And so the ultimate goal of all of this is to essentially find a way to develop something that's adaptable and robust enough to be easily applied to our systems. I know that right now, Apple is working on on this sort of technology for our phones, which is much more small scale. So I'm more interested to see what they're doing than what these EV cars are doing. I don't know if anybody has noticed on their phones. I know Apple does it. I don't know about Android, but when you set when you charge your phone, let's say at a certain time, and you have your alarms on, it will tell you, hey, we're going to charge until 80% up to time, let's say 4 a.m. because we know you wake up at 6 a.m. So we'll do the rest of the extra 20% closer to 6 a.m. So what they're doing is basically extending the life of the battery on your phone. We didn't have this before, and so that's why a lot of these phones they're lasting much longer than they used to in terms of battery. Now, there's other reasons why they might not last long, but besides the point, the battery itself is much more capable now. And so being able to translate this into different fields will be really interesting to see. I think it's really exciting, and I hope people got something out of this. I hope I didn't overload people with a lot of information, but it just is. That's the nature of this work. But that's all I have. Yeah, I forgot to mention this sort of technique is also being used in manufacturing. Using machine learning and intelligent based methods to detect those defects during the building process of a battery before it actually gets built. France has a huge group called the Artistic Group. It's a big collaboration between different universities, and they've gotten the furthest I've noticed with this kind of work. But I think that is the most interesting thing out of all this. But we'll see where that goes. But yeah. Yeah, I see it. So he's asking, when do you determine when to use ECM versus like physical models? That is dependent on the hardware that you have. If you have the computational luxury to perform those kind of those huge models. What determines it is usually time. If you're in a company where you're a startup and you need to have a product really fast, you might just go with ECMs. If you don't really care about the physics behind it and you just want something that lasts just a little bit longer, you might just use ECM. It's just a preference. So depending on how precise you want to be, essentially, because there's a certain limit to how precise your predictions can be with just ECM rather than physical models. But the other determining factor is that ECMs have been used for a while, and so there's a lot of resources online on how to actually implement them. There's a lot of people that have already implemented them. The physical models are relatively new, maybe within the last 10 years have they been used or researched at least, and there's still a lot of work on how to make it easier for us to implement it and how to actually compute them. So that is also another factor, but until now, it's usually just ECMs plus some sort of heuristic knowledge that people have that are implemented. So in the future, it will just depend on the hardware that you have. Maybe you know how to implement the physical models, but the hardware you have at your company or your group is just not capable, so you can't implement those. Ideally, you would have the physical models all the time, but okay.
It's nice to see control theory in other industries.
Oh, definitely. Yeah, I think control theory is usually seen as something you see in industrial places or robotics, but it has much more uses than people think. Yeah, usually you just see it as a PID, multiple PIDs. But we're getting closer and closer to using more the, I guess you would call, modern control techniques, such as this one. Yeah, yeah. That's just straight up space-based models. This is the nonlinear version. So as you can see, you have a function that is reliant on the different states. So it's not like a linear, like most of us are used to seeing, like ax plus bu. A times x equals xk is something that makes it linear, but this is not that. We have an actual nonlinear function defining our states. So it's a little bit different, but it's essentially the same thing. We have our state transition matrix, we have our states, we have our input matrix, we have our input u, and then this is just some sort of noise. This is a stochastic process. So there is some sort of noise. Typically, is assumed normally distributed. And so that gives you the uncertainty that we don't actually have in sort of like an ideal situation.
Get blocked.
Hi, I have a question.
Sure.
First of all, thanks, Sois, for a great presentation. I was just curious on how you got into this lithium ion industry.
Actually, I'm not really sure. I just applied to a position at my current job. There was a different department. It just said electrical engineer, design and test engineer. It didn't really talk about batteries. During the interview, they asked me if I knew anything about batteries. I said no. But apparently, the whole entire job was within batteries itself. And so that's what I did for the past 2 years. And now I was doing abusive testing on batteries, different sort of batteries, but that's how I got into it. It was just out of the blue.
Okay, cool, thanks.
No problem. If anybody is actually interested in lithium ion stuff, if you ever go on LinkedIn, just type in like lithium ion and look at groups. There's a lot of both not just LinkedIn groups, but like international groups that conduct little meetings and get-togethers. There's one called Battery Lunch and Learn or something like that. I can't remember. But every month or so, they have like 2 or 3 meetings. Everybody just gets on Zoom, and people they're from all sorts of like knowledge base on batteries. So you have people that just got into it, people that've been there for years, and they just talk about different technologies in current industry or their own experiences and whatnot. But I think that's one good way to get into it. Oh, thanks for having me. Oh.